And I think, if I understand well, we are moving from modeling to geotechnical characterization. Thank you, Hauke, once more. And I will use one of your figures in lecture tomorrow if I can. I took a photo.
Okay. Well, hello everybody. First of all, I would like to do a disclaimer here about the authorship of the presentation. This work and the presentation is done by my colleague Enrique Sanza. I'm not really related with this work and only the spokesman. So I will appreciate if any comments and questions will address to him. At the end of the presentation, we'll give you the contact data of Enrique, because I'm not really in this topic and it's a little bit difficult for me. The second disclaimer is about the topics. It's not, we are not dealing here with a topic that is completely related with offshore geotechnics, more with marine or sea engineering. And this is a picture that I tried to explain why in Spain we are a little behind in the development of all this offshore structure, maybe because we don't have this extensive continental platform that we have in other countries in Europe. So all the development of this offshore structure is a little behind compared with the rest of Europe. But on the other hand, we have a lot of coastline, so we have a lot of experience dealing with these soft soils or ultra soft soils that we can find in these marine environments. Here is a part of a table when I try to frame all the kind of materials we are talking about. We are talking about the materials that are almost water, almost all liquid in the part, and the transition between dense mud and a soft soil that is more conventional in geotechnics. This material is sometimes close to the liquid limit in the water content, and is very, very low shear strength compared with other kind of soils. This material is quite related with all these topics that we are talking now, not directly maybe, but in all these high infrastructures that you present, sometimes involve the dealing with this soft soil that we can find in the first meter or so of the sea bottom. Here we can find this when we are dealing with things like pipes or wires or things like that in the nearshore environment. Well, this is the different approximation that we can use to deal with the geotechnical characterization of these kind of materials. But none of them are quite adequate to these ultra soft soils. All the sample that you can collect from this material will not be undisturbed at all, so we can use it for the lab testing. And some of the common in situ testing that we can use, as CPTU, for instance, that is a very good technique, it is not quite reliable in this first meter because of the lack of strength in the material, and for the vertical load is very, very low. So we think on another way to deal with the characterization of these materials, and we thought in a test that we can perform in the lab, that is the falling cone. And we thought, why not to do this test in situ? And we sample, we think that we can do a big cone and dealing with the problem of the buoyancy and other problems that we can find in the underwater environment. We develop and try the use of this equipment to characterize this first meter or so of material. These have a very strong theoretical background that we can adapt and use for this material. We can. It's very inexpensive. You can do build one of these for very low money, and you can do it within the facilities of a port. That is something we have done before, and it can be operated by dives, a diver like you can see there, or from a vessel if we have deeper waters. Well, this is a theoretical background that you almost, I'm sure you know well. It's based on the theory that it's built for the phone call in laboratory. That now we have an ISO standard for that, and simply we use this theoretical background that already exists to address our equipment. Well, the theoretical background is based on the analysis of the plasticity of the soils, using the method of the characteristics that is here is an examples. This is almost the hypothesis of this theoretical background, the basis of our Coulomb with an associative rule, and it can be used both in clay materials and in sand materials. As you can see, I'm a little bit quick because I'm not completely sure of what I'm doing in some terms. Sorry. Well, this is the method that the theoretical background for undrained behavior that is solved by Hasley in 1980s, and this extend for another uses in 2003. And you can see that it's the same method that we can use for CTPTU. Looking for the equilibrium of this cone in a plastic material, we can find this gamma that is related directly with the strength or the shear strength of the material. Yeah, this is more or less well is according to the dimensions of the cone we used. This is the parameter n gamma that we have, the constant of the equipment, and easily we can determine the S sub u, the undrained shear strength of the material, measuring the weight of the cone that we already know. We can change the way according to the conditions we expect in the material, and there according to the how deep the cone will reach the equilibrium in the soil. We can work with different laws, or we can do different approximation on different tests of this different configuration of the test to check if we are doing correct calculation. Well, this is all, almost the same. Well, no, this is related. How can we change the angle of the cone? And in our case, we are working with a cone of 30 degrees. Okay, nothing on here. Well, this method is also useful for the study of the material in drainage behavior, like sandy soils, and the method is almost the same. That is, the theoretical study was done in 2002 by Cassidy and Hasby, and it's published in Geotechnical. And the method is quite similar. We get another parameter, and this is this n gamma that is directly related with the friction angle of the soil. So in the same way that we are doing in the undrained behavior on undrained materials, on clayly materials, we can get this strength parameter, in this case, the friction angle, studying how deep the cone reaches the equilibrium. Well, this is a simplified a simplification of the calculi that we done in our department for an easy way to calculate this friction angle with an error done less than 0.5 degrees with this approximation that simplify a lot the calculus. As you can see, it's almost the same that okay. And this is almost this is the details of how our Wicon has built. We built 2 prototypes that we already tested and we already used. It's made on aluminum, and almost 1 meter high, and as I said before, 30 degrees of the cone angle. The submerged weight is about 7.5 kilograms, and it's equipped with a buoyancy cell that prevents all the tilting and helps in the installation of the equipment. We can change the, as you can see here, we can change the weight that is stored inside the cone, because we can adapt this the same equipment to different materials. In case we have more or less strength in the soil we are testing, we can change these loads before the putting underwater, or even in the top. This is the other. This is the prototype one that we use in clayly materials. This is the second one. That is, as you can see, 2 different equipment, but almost the same procedure, because it was cheaper to build that in the harbor facilities than to transport it from one to another. And in this case, there was a diver in the bottom of the sea taking the measures. We already have these pictures. In this case, it was automated, perform the test, and we all control this, how deep was the cone by a camera from the surface. Well, the cone was coated with a water-resistant grease to smooth as much as possible the surface and get as closer as possible to the theoretical background. As we say, it could be operated from the vessel or handled by a diver, because of it's a low weight of the equipment and it's easy to move. Okay. This is some tables that we perform on how, according to the weight of the material, of the cone, sorry, and the penetration of the cone, we can get directly, in this case, for undrained strength, the undrained strength of the material, and in case of drained materials, we can get directly the angle. As you can see, we can change the weight, so we can perform the test trying to do a penetration that is almost in the middle of the cone to ensure that avoid any problem with the theoretical background. This is 2 examples on how when we use. This is from frictional soil. As you can see, it was a volcanic sand that it was a very high angle of friction, sorry. And the other one was using a cohesive soil in a clayey material in a Herror in the north of Spain. And this almost everything. We present here a device that is easily used to determine the geotechnical characteristics and the resistance of a soil in a very soft soil with a strong theoretical background. What support that? And so far, it was proved to be fairly in agreement with our laboratory tests and our previous data. And here are the contacts of my colleague, Enrique, if you want to say something about this work.
Thank you, Mauro. Thank you very much. So we can direct the communications and the queries to Enrique also.